And so far I've had to admit everybody that has joined us. So you're surely all, excuse me, you're surely all not signing in uh, with some account other than your school account. So I'm seeing the normal background images that I see. So I'm guessing pretty much everybody's signing with their school account, and there's something funky with Google Meeting set up. So, all right, whatever. And the dog wants in. So the screen is recording the video on the non-student side. So none of your images or voices are going to be recorded or are being recorded. When we're done, I'll put this recording in the lesson plan. So there's that. Yeah, nope, I have to admit, bugger. So the lesson plan for the day. There are a few notes to run through on electric energy, on power, and the loop rule. And then a brief review on how to do the electric circuits at home activity. That's the activity from Friday last week. Um, uh, it's a little bit, that one's getting, seems to be a little bit slower for folks to turn in. And oftentimes I feel like when that's the case, it's probably because it looks weird or there's something about it that feels funny. So people have a tendency to not jump into the funny feels. I don't think this will take us too long. I think you might end up having plenty of time. We might finish before 11 is maybe a way to say it. So we'll see. And then you'll have some time to work on the other assignment that we've got. In the classwork section, you have where did I put it? Oh, this here is a note sheet. I should put the word note in there. My apologies. I'll do that now. So there's like a blank note sheet where if you have access to a printer, you could print that out. Oops. And you could kind of use that to write notes in and things like that. Of course, you don't have to print that out. You can just write notes, pencil paper on a notebook. I'm not going to be checking notes. You don't have to turn them in, but oftentimes it's really helpful. Just the act of writing things down and thinking about what you're doing while you're writing them down is even more helpful sometimes than most of the time. Oftentimes it's more helpful than just kind of going through and trying to answer a couple of questions off of a video. So some of the notes stuff, I'm going to try to zoom in so we have a digestible chunk on the screen at a time. Oh, that's too far. Let's see. Yep. There, that's about right. Hello. So electrical energy, and we've talked about this in other ways earlier, but an example or a way to talk about it now is it's just in terms of a definition. Hello. In terms of a definition, we can think of electrical energy as being energy due to charges that are interacting with each other and maybe moving other charges. An equation, if we take power times time, power is how quickly we use energy. So if we take power times time, that ends up giving us this electrical energy or energy in general. And maybe I'll do this. I'm going to put a parentheses around this bugger. The current times the potential difference is the same thing as electrical power. So we're saying another way to calculate this is to say that energy is electrical power times time, current times the potential difference. And if this is an equation, things like that, we would just say big E with the subscript E. This one wouldn't be bold or italicized or anything like that. This is energies are just an amount. There's no direction to them. We've talked first semester and a little bit this quarter with how some things have a direction, and so we'd say to the left or to the right, or positive or negative. And it's possible to have positive and negatives for energy, but that has no indication at all on the direction, really just purely amounts. And all energy is in the metric system measured in joules. Electric potential, or aka voltage. Energy per charge, we've done this one before. So one way to think about it is it's the electrical energy divided by charge. That's one calculation, totally legit calculation for electric potential or voltage. From Ohm's law, if we rearrange Ohm's law that we did with, we started off looking at Ohm's law as current is potential difference over voltage. If we rearrange that, we can solve for voltage, and we've got her there. If we take the relationship for power and we rearrange and solve for voltage, we've got that one there. And then there are, again, a bunch of different ways to rearrange and solve for different things. Like if we solve for current here, we could then put that in here and different things like that. It gets to be, there are a lot of different substitutions and things that we could do. Need to admit somebody. There we go. What else? There is one other way, like if you're ever looking this stuff up, there's a weird script-y sort of a version that people will sometimes talk about for electric potential. They'll call it the electromotive force. I don't know if I can find a good font for that. I wonder if their capital E would do it. Yeah, that's pretty close. So that is sometimes referred to as an electromotive force, which is the same thing as electric potential. And volts are the same thing as joules per coulomb, or energy per charge. Potential difference, just the difference in electric potential or the voltage at two different spots. We've looked at that already. Excuse me. Then mechanical power. Mechanical power is how quickly mechanical energy, like gravitational energy, kinetic energy, those sorts of push and pull sorts of things where you think about maybe physically grabbing something. Mechanical energy or mechanical power is how quickly mechanical energy ends up getting used. Excuse me here. Oh, so I remembered to mute the mic for you, but the recording, not so much. Well, sorry, clearing my throat there. So the electrical, or pardon me, mechanical power, power is energy over time, how quickly that transfers. Symbol and equation would be P, and power is joules per second, energy per time, joules per second, and that's the same thing as a watt. And then we've done an assignment with this sort of a thing before. And I just wanted to make sure we had it recorded in a note, set of notes sort of thing somewhere. So we've talked about the loop rule, and I'm just adding the two terms, the two words, electric potential loop rule up on top here. So the electric potential loop rule says that if we go around a loop, the total electric potentials as we go around them, if we add those electric potential differences as we go around a loop, they should add to zero. So the outer orange loop, there's that orange line isn't quite as obvious, but there's an orange line on the outside here. So if I follow that orange loop, if I start around here, I've got a potential difference provided by the battery. And then the charges that take this outer path, there's a potential difference used by the light bulb, and then we get back. So if I do the potential difference, or if I do the potential difference for the battery, that should be positive. It's giving energy to the charges. And I add to that the potential difference from that top bulb in the orange loop. That should be negative. That top bulb should be taking energy from those charges. If we add those up for a loop, it should add to zero. And then if we do this for the bottom loop, the same rule still works. If we do this for this bottom blue loop, we gain some energy from the battery, lose energy going through the bulb. And as we add those potential differences, they add to zero. And remember, this is the energy at a location. And sometimes I think it's helpful to think about just following one charge, because one charge can only take one path at a time, right? So if we follow a charge that starts in the bottom right corner down here, let's see, I'll try to do this. That starts in the, whoops, let's see, there's a way to, nope, that's not the one I wanted. Darn it. There's a keyboard shortcut that I often use that is the way to zoom in on this darn spotlight. Well, I'll leave it as it is. So if we're looking at the bottom corner here is where we're starting as a charge's location. That charge then goes through the battery, gains potential, goes through the wires have no effect. And then if we say this one charge in particular then goes to the right, as that one charge goes to the right, it loses energy going through the bulb and then goes back to the battery and starts that process all over. So that charge can only take one path at a time. The next time through, it might go through the battery, gain energy, then go all the way up to the top and lose energy going through this bulb, but it's, you know, per path, we have this rule that really seems to hold true. Um, and electrical power. Uh, Electrical power is how quickly electrical energy is transferred or used. It's not always how to say it. It's not always 100% used for what you would like it to be used for. In some cases, that electrical energy goes to doing what we want it to do, but almost always it also produces maybe like a little bit of heat or something like that. Like if you ever charge your phone or your Chromebook or whatever other devices you have, you might notice sometimes that the little charger gets warm. Well, that's not a desired outcome. That's not something that is intended to happen with that electrical energy. It's just supposed to charge your device. Um, Electrical power, we talked about it or referred to it briefly up above. That's the potential difference times current. And if we remember that 1 volt is 1 joule per coulomb, and current is measured in amps, and 1 amp is a coulomb per second, we can see that a joule over a coulomb times a coulomb over a second, those coulombs cancel and we get joules per second, which is a watt. So our units still work. And that's one of the ways in physics we can kind of double check to make sure that we're not just making stuff up. Hey, the units end up working out. This seems like a reasonable thing. And so if we look at the equation for electrical power, one way to calculate it is like that. If we use Ohm's law, and in Ohm's law, potential difference is current times resistance. So I can sub in that. Another way to calculate electrical power is this, I squared R. And lastly, I guess maybe not lastly, there are probably some other ways we could go through and substitute, but for us, this is probably the last one. Electrical power could be the potential difference squared divided by the resistance power, and joules per second or watts. This last one we might not use. We're definitely not using this one today. We might use it in the future. There are a couple of things that we've done in the past. I'm just throwing this on here because it's a reasonable thing. So efficiency compares the energy we put into a job to the energy we get out, or the usable energy that we get out. And it's always less than 100%. That's just always true. No matter what you're doing, there's always some energy that becomes something that we don't want it to do. Again, like I just said, with charging things, we always often produce a little bit of heat, things like that. So the energy, or pardon me, efficiency is a percentage. So it's a percent efficiency. And it's usable energy output goes on top, and total energy input goes on bottom. And then we just multiply those two times 100 to make it a percent. And that's that. Alrighty. And then when we're done with class here, I think I have this set of notes. I should change this to the word notes up in front. This is going to be available on Google Classroom after class time here too. So you'll be able to check that there. Alrighty, then I'll leave that there for a second for folks that are still working and maybe copying some stuff down. The next thing that we're going to look at is the that electrical energy at home stuff. That assignment that was given on, I think it was given on Friday. Some folks found it to be not as bad as the power as the Google form that was given on Thursday. But again, like I said before, I'm guessing that since there were so few people that turned this one in, or I shouldn't say so few, because a lot of you did. Since it's not as, I'm not getting as many of them in on time as normal. That makes me think that there's some confusion about this. So I want to go through, take some time to look at this and talk it out. I'm working on designing another assignment that has a similar sort of layout to it. And so it's worth taking some time to make sure things work. So just to make sure electrical devices at home, we're going to just get some data from the devices that you have in your house. Those things have a potential difference from plugging them into an outlet. And most of the outlets that you're plugging those things into are at 120 volts. Um, there are some outlets in some houses that are arranged a little bit differently that are actually at 240. But for most of the things that we're looking at, we're talking about 120 volts. And the voltage range. Oh, I've got a guy that's looking to do some work on the house. I'm Sorry about that, guys. Um, so uh, totally threw me for a loop. All right. Yeah. Um, so the voltages for most things are 120 volts. The power ratings are usually on the bottom or the back of the device. Um, and you just record the power values here. That needs to be numbers only. There were a few folks that were putting in things that included the letters for watts, and it can't do calculations if you do that. If you put in uh, numbers only, this thing will calculate and tell you if you got these answers right, like within a reasonable range. Um, and so let's say like my toaster, if I look on the bottom of my toaster, it's 900 watts. If I just leave it as 900 and enter, then that works. If I put it as 900 watts, yeah, that won't work. So my toaster is a 900 watt toaster. It plugs into the outlet at 120 volts. You guys can't type over here, but the way I set this up, I can. So power is the potential difference times current. And down here, I'm going to try to solve for current. So if I use this to solve for current, I can say, hey, I want to get rid of the potential difference or the voltage. There really should be a delta V in front of there, that little triangle, but I'm not going to worry about that right now. So I want to keep current there, and I want to get rid of the voltage or the potential difference. So I can just do a divide by V, and that removes the voltage from this side. And if I do that to the other side, divide by V, now what I have is power divided by potential difference equals current. And the math department, again, usually likes the thing we're solving for on its own, so we'll placate them. So now if I say current is 900 watts divided by 120 volts, I don't know why that keeps going to the thing there. Now, if I punch that into my calculator, calculator, come on, calculator. Okay, 900 divided by 120 equals, I get 7.5. So if I go down here and punch in 7.5, enter, come on. Oh, you're kidding me. That should turn purple. Why is that not turning purple? What did you do? Did I not hit enter? I hit enter. Ah, it worked yesterday for everybody. I just made a copy. Maybe I didn't copy everything over quite right. But then, yeah, that copied that down. So when we go through and do those things, that should end up working out. Numbers only. Then if I go down here and I calculate the resistance, you see that the score went to 5. So it did calculate your score correctly. So it didn't highlight it, but hey, it is what it is. I'll work on fixing that here. I just made some changes on this one. But if you go through and put your numbers in here without the text, without any letters, it should be just fine for going through and calculating things out and telling you if your answers are correct or not, at least with the score up here, if it doesn't change colors here. So that's the gist of it there. I suppose we could go down here and do, oh, darn it. We could go down here and do an example of calculating resistance. So as you go down, you'll notice that when I put the 900 watts up above, it then also copied that down here. When I put the 7.5 here, it also copied it here. So the numbers are being placed everywhere you need them. So now we have electric potential, we have power, we have current. To find resistance, I'm going to go up here and use this as a little workspace again. To find resistance, we can use Ohm's law, and that has current and resistance and potential difference. So I need to get resistance out of the bottom part of the fraction. So if I multiply both sides times resistance, that gets, at the very least, resistance out of the bottom part of the fraction. And we end up with this. Excuse me. And now we need to get rid of the current that is there, so we can have the resistance by itself. And so I'm multiplying those two to get rid of current. I'll divide by current. Oops. And if I divide by current on one side, I need to do that on the other. So now I get resistance is voltage divided by current. And for this question, the voltage was 120 volts and the current is 7.5 amps. Come on. Divided by 7.5. So now if I plug in 120 divided by 7.5, floop, I get 16. So if I go down here and I put in, oh, come on. There we go. So 16, and then we'll see our score went from 5 to 6. So that's a shot that we did that correctly. It should also give you a little bit of wiggle room. So like if there's some rounding that needs to happen, you can round numbers off to a reasonable value, and it should end up letting that happen, letting that work okay. All right. Then when you're done with this, you should end up seeing your score here. If I end up changing things and I put like just even this one as 900 watts and I hit enter, you'll see this score goes down because it can't calculate. As soon as there's a W in there, it doesn't, we've confused the computer. Computers can't calculate with a W, right? They can calculate numbers really fast, really well. They can't calculate letters. So I remove the W and it goes back up to a 6. So just that little warning. And the same goes for all of these cells too. These need to be just numbers here. That's why in the data table we put those units of measurement up above. All right, that's a lot of stuff. That's what I got for you. So we've gone through notes. We've reviewed how to do this. There's one more Google form assignment. That's a 6-point assignment. It has just a few questions based off of a video that's maybe like an 8 or 9 minute video. So if you watch that 8 or 9 minute video and you answer those questions, um, you should be good. That's what I've got for you. I'll hang around if you have any questions. Um, I don't get the W equals V plus V deal. Oh, now I do because I'm slow. All right. If you have any questions, let me know, and I'll hang out here to see if anybody has any questions. See you later, folks. So if you got to go, you got to go. If you have a question, ask your question. Yes, sir. Yep. Exactly right. Yeah. And so you can either click on this link or you can click it's right down on the bottom here too. And then this has links to just a bunch of them from Target. You can just pick a toaster and it shows that down on the bottom. Um, so if I go there, toaster, 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 Target has your toaster. Target has your toaster. Dry bread. Come on. It's going slow. But then when you go there, there's a little like more data thing. Hey, so slow. I'm just going to pick this one because it's right there. And as I scroll down on details here, and then there's show more. Clicky. And then they say wattage output 900 watts. So that toaster, 900 watts, just like my toaster. Okay. We'll see you. Have a good one, man. Thank you.